All right, let's dive into a topic that is just mind-bending. We're talking about quantum computing. You've probably heard the term thrown around, and it promises to be this next massive revolution in technology. But to really get what it is, we actually have to start with the computers we already use every single day.
So why do we even need a completely new kind of computer? Well, it's because the amazing machines we have right now, from the phone in your pocket to the most powerful supercomputers on Earth, are starting to run up against a fundamental wall.
And what kind of wall are we talking about here? Look, it's not about making your emails send faster or your games load quicker. We're talking about a whole different class of problems, ones where the complexity just grows at this explosive exponential rate that our current computers just can't handle.
This slide nails the difference perfectly. On the one hand, you have something like figuring out the best route for a delivery truck. That's complicated for sure, but it's manageable for a classical computer. But then, ask that same computer to perfectly map out every single quantum interaction inside a complex molecule to, say, design a new life-saving drug. The number of possibilities just explodes. As it turns out, trying to simulate quantum physics on a classical computer is, well, kind of an impossible task.
So the solution is to build a computer that actually thinks like the quantum universe it's trying to simulate. And the absolute key to doing that is a totally new kind of building block, the quantum bit, or as you've probably heard it called, the qubit.
And this is where things start to get really weird and wonderful. The computer you're watching this on right now runs on bits. You can think of them like simple light switches. They're either on, which is a 1, or they're off, which is a 0. That's it. Simple, right? A qubit, on the other hand, is more like a dimmer switch. It can be fully on, a 1, fully off, a 0, or, and here's the quantum magic, it can be in a blend of both states at the exact same time.
This whole both-at-once ability has a name, superposition. The classic analogy is a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's neither. It's kind of both. It's in a superposition of all the possibilities. It's only when you measure it, when that coin lands on the table and collapses, that it finally picks a side and becomes either heads or tails, a 0 or a 1. That's the first superpower of a qubit.
But believe it or not, it gets even weirder with something called entanglement. This is where you can take 2 or more qubits and link them together in this really mysterious way. Imagine you have 2 of those spinning coins, but they are magically connected. The very instant one of them lands on heads, you know with 100% certainty that the other one, even if it's on the other side of the universe, has just landed on tails. Their fates are completely intertwined.
So superposition and entanglement, they're not just weird party tricks for physicists. They are the twin engines that drive quantum computing. When you put them together, you get a machine that can explore a massive landscape of possible solutions all at the same time. Let's take a look at what that power actually looks like.
This is where your brain might start to hurt a little. 100 classical bits can store, one number that's 100 digits long. But 100 qubits, because of superposition, their combined state represents 2 to the power of 100 possibilities simultaneously. That's the number you see on the screen. It is astronomically huge. Every single time you add another qubit, you literally double the computer's workspace.
Okay, so what in the world could we do with that kind of horsepower? Well, for starters, we could run algorithms that could, theoretically, break most of the encryption we use to protect our data today. But on the positive side, we could finally simulate those complex molecules we talked about to design revolutionary new drugs and materials. We could solve enormous optimization problems for logistics or finance, and we could potentially supercharge the fields of AI and machine learning.
And this isn't just a science fiction dream. This journey really kicked off as a serious idea way back in 1982 when the famous physicist Richard Feynman first proposed it. Then, in 1994, Peter Shor discovered an algorithm that could break codes, a potential killer app that got everyone's attention. And more recently, in 2019, Google claimed a huge milestone, something they called quantum supremacy, with a machine that did a calculation that they said was basically impossible for any normal supercomputer.
So, that sounds incredible, doesn't it? The revolution is practically here. Well, not so fast, because for all of its incredible, mind-blowing promise, actually building a useful, large-scale quantum computer is one of the hardest engineering challenges humanity has ever taken on.
This quote from an article in the prestigious journal Nature really brings all that hype crashing back down to earth. It basically says that while the future potential is huge, right now, for solving actual practical problems, today's quantum computers aren't really useful yet.
So what is the big problem? What's the holdup? Well, the main villain in this whole story is something called decoherence. That delicate quantum state a qubit is in, it's unbelievably fragile. The tiniest vibration, a little bit of heat, a stray particle from space, any of it can make the qubit lose its quantum magic and decohere, which completely ruins the calculation. It's like trying to do complex math on a chalkboard during an earthquake.
And fighting decoherence leads to this absolute mountain of engineering challenges. To make this work, scientists have to figure out how to create and control millions of stable qubits. They have to keep them almost perfectly isolated from the outside world, often inside refrigerators colder than deep space. Then, they have to make calculations faster than the errors can pile up, and on top of all that, they have to build incredibly complex error correction systems to fix the mistakes that still manage to sneak in. It is a monumental task.
So you have this tension, right? On one side, you've got this mind-boggling potential, and on the other, you have these staggering, almost impossible-sounding difficulties. This really defines the current state of quantum computing. So let's talk about where we actually stand today.
Let's circle back to that quantum supremacy claim. Google said their Sycamore chip did a very specific, tailor-made calculation in 200 seconds that would take the world's best supercomputer 10,000 years to do. Huge news! But then IBM shot back saying, hang on, if you use a smarter classical algorithm, our supercomputer could actually do it in just 2.5 days. So this whole debate just shows that the finish line, the point where quantum truly pulls ahead for good, isn't quite as clear as we might think.
All of this brings us to where we are right now, in what experts call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Intermediate scale is the good part. It means we have machines with dozens, even hundreds of qubits, which is amazing. But the key word here is noisy. It means they're super sensitive to that decoherence we talked about, making them really error-prone. They're powerful enough for some really cool experiments, but they're not yet reliable enough for those huge, world-changing applications.
And so that leaves us with the ultimate question. The physics works, we know that, and the potential is truly astronomical. But the engineering challenges are just as massive. So is this the dawn of a new computational age that's going to reshape science, medicine, and technology? Or will the problem of noise and errors keep these powerful machines a distant, specialized dream for the foreseeable future? The truth is, the race is on, and the answer is still being written.